Welcome everybody. Today is actually our fourth presentation in the Ontario Science Students Association lecture series. So I'm pleased to welcome Dr. Stephen J. Rehse, who is a professor of physics and is also currently the head of the Department of Physics at the University of Windsor in Windsor, Ontario. He's been at the University of Windsor since 2011 and conducts research into the use of the laser-based spectrochemical analysis technique known as laser-induced breakdown spectroscopy, particularly to analyze samples of medical interest, most specifically pathogenic bacteria. So without further ado, Dr. Stephen Rehse, and I'll hand things over to him now.
Okay, thank you so much, Griffin, for the nice introduction. Thank you, everybody, for joining us. We're lucky that the first couple minutes of the presentation don't necessarily have technical content in it. So if people keep trickling in as they can, I don't think they're going to miss anything. So thanks everybody for joining us on this. I hope you guys find this talk kind of interesting. It's as long as it's science students I'm talking to, there's a lot in here about different disciplines of science. So I've really found that this application that I've kind of found myself in is really, really interdisciplinary and appeals to kind of a large swath of different scientific fields. And it's actually one of the things I've enjoyed most about the type of research that I do, which is engaging with people who are not just physicists. So I hope, rest assured that for those of you out there on the Zoom land who are not physicists, I believe you're going to be able to get something about it. I'm not looking at the chat or anything. I know you guys have all given Zoom presentations before when you're running this full screen thing. So if you have a question, if you could just unmute yourself and say something, that would probably be better. Or if you chat, I mean, I suppose Griffin could always like stop me there too, but I'm not even seeing the chat. So if you can just ask it, that would be fine. It won't bother me at all to ask questions during. And if you have something that you really want to know pressing, I think that'd be the best way to do it. So you won't bother me at all or throw me off if you have a question about this stuff. So without further ado, let's get into that. So we start with our land acknowledgement statement. Very important just to recognize that where we are here at the University of Windsor, we're sitting on the traditional territory in this part of Ontario, the Three Fires Confederacy of the First Nations. That includes the Ojibwa, the Ottawa, and the Potawatomi. We respect the long-standing relationships with the First Nations people in this place and the 100-mile Windsor-Essex Peninsula and the Straits or Le Detroit of Detroit. So we're very glad to be able to share this land and share our time on the land with you all today. So I have some slides that, for people in Ontario, I don't know where you're all coming from. If you're at MAC, you might know this, but I do realize that not everybody knows where Southwestern Ontario is, particularly when I travel throughout the United States. Nobody knows where Southwestern Ontario is. So I figure it's always good to at least ground ourselves and know where we're talking about. So of course, that's North America, that you all know for sure. We can zoom in on that a little bit. So if you zoom in on Southwest Ontario, really talking about the area of Canada that borders Detroit. And I'm showing Detroit, Michigan, and Windsor is right across the river from that. So if we zoom in on that, so anybody who knows anything about Windsor knows that Windsor is the one part in continental North America where Canada is due south of Detroit. So I'm actually showing the Google Maps here with north is up and south is down. So Windsor really is south of Detroit. So it's kind of funny, I'm actually American. So when I talk to Americans, they think we live in igloos and things like that. Sometimes I say, hey, we actually live south of the United States. And here we actually are. So I'm talking to you from the University of Windsor. Down here, it's right on the river. And if you could get up on the roof of my building here at the University of Windsor, you could look across the Detroit River. I'm actually almost looking out the window at it right now. But if I was up on the roof, I could probably see the building where I worked at Wayne State University from 2005 to 2011. I was a professor at Wayne State. And we're about 3 miles apart, basically, as the crow flies. And this project I'm talking about here really began at Wayne State, and now it has continued here in Canada at the University of Windsor. So when I was at Wayne State, I had this idea, this hypothesis, and I'll kind of give you the genesis of the idea as we get into it, which is, can this all optical technique of LIBS, and I'll define what LIBS is in a bit, it's all optical. You shoot lasers at things and then you just collect the light. So you don't have to touch it, and there's no chemistry to it. You don't dissolve things, and there's no acids. Can this technique really identify a bacterial cell or a bunch of bacteria, and can it do it in under a second? so that's just the hypothesis, and that's kind of turned into my life's work, this idea of, can you walk into a clinic and they can shoot a laser at you and they'll identify what you're infected with in like a second. I mean, I'm nowhere near that now, but that's the goal. And when you're in Canada working and you're trying to get funding, and you guys might be doing this someday, you have to have a vision for your research. It's not just, what am I doing day to day? What are you doing big term? What's your vision for where this project could go? So this is my project. Is that possible? Don't know. That's my hypothesis. But 8 publications later, confirmed by multiple other groups around the world, it gave me to belief that could it be possible? Yes, it really could definitely be possible. And then in 2011, I came across the river and started a research program at the University of Windsor. And my research focus shifted from answering that hypothesis, which is, can this technique actually do it, to, can we actually translate the whole technique into something that's actually practical, could really be used in something that's convenient, easy to use for a clinician kind of test? Because of course, those two things are very different. Many of you have probably taken the COVID tests on those little sticks, and there's a huge difference between the COVID test on a stick that they give away at the Shoppers Drug Mart, 5 in a box for free, versus a huge microbiology lab down the hall that costs $10 million and requires an army of PhDs to run. So the one, yes, they can have a test, but if you can't make it simple and broadly usable, it's just not that useful. And that's where we are with this project right now. My students and I just trying to figure out, can we consolidate our knowledge down to a point where people could actually use it? That's turning out to be the really tough problem. And that's going to be probably, the focus of my research for many years to come here in Windsor. So that's kind of what I've been thinking about. So I put a question mark there. I don't know, that's the work. So you guys are hopefully doing some sort of research in your labs. There's work to be done. If it was all known, it's not research, that you'd be working at a company. So we're trying to figure it out. So let's give this the outline of the talk. That's kind of my motivation for what I do. So I want to talk to you about this method, LIBS, which I hope sooner or later, somewhere down the road, some of you might encounter or have some run-ins with it, because it actually is being used in many, many different areas of science, not particularly physics, science and engineering. I'll quickly talk about some of the advantage this technique has over some of the other methods, and then I'll get into kind of a review of what I consider to be a new paradigm for pathogen identification. So taking microbiology out of the microbiology lab and kind of bringing it into the spectrochemical, physicist, engineering, analytic chemist lab. Okay, it says I'm being signed out because I'm signed in on another device. So I'm assuming I'm still signed in. So
we can still see and hear you. So
okay, that's weird. I just had a message pop out saying I was being signed out of Zoom. So I don't know what that means. So again, Zoom is doing some weird things for us today. So I don't quite know what that's about, but all right. So let's get to this thing then. So we're going to, the primary laboratory that I use is this thing called a laser-induced plasma. So let's talk about laser-induced plasma and say, what is a laser-induced plasma? Well, I think physicists, we have our flaws and we have our faults, but usually we're pretty good at naming things. So a laser-induced plasma is a plasma which gets induced by a laser. So that's a tautology, but it's really true. It just means that you take a short little pulse of laser light, and I have a cartoon animation on the screen. You focus it down modestly, it's not super expensive. The lasers are kind of expensive, but the lenses are just simple lenses. Focus it down to a spot. And it turns out that the energy in a laser pulse is so high that when that laser pulse interacts with a target, it kind of blows it apart and it forms this thing called a plasma. And I'll define what the laser pulse and the plasma is in a bit. But a plasma is this superheated ionized ball of gas. And this is a real picture. So the red thing's a cartoon, but this thing on the right here, this is a picture that I took in my lab. And that plasma is about 50,000 Kelvin. So 50,000 degrees Kelvin or 50,000 Kelvin is what you say. And that's 5 times hotter than the surface of the sun. So it's a really hot little ball of gas and it gives off a lot of light. And that you can do then something with that plasma. Some people are trying to make fusion confinement in these plasmas. We're using it to kind of do spectroscopy and chemistry in it. But this thing here is a laser-induced plasma. And since this is not a physicist group and you guys are all Ontario science students, I can tell some of the funny things that have happened to me in science. And I realized when I was at Wayne State and I had submitted all my safety paperwork to do these experiments at Wayne State, I think some of my reviewers were about 2 pages into my proposal for could I do this work safely in my lab before I realized, I think they were they thought I was talking about blood plasma. which I bet for some of you on the line, that's actually what you think of when you do plasma. If you're a med student or if you're in biology or chemistry, you might be talking about blood plasmas. This is not that kind of plasma. That's the plasma in your blood. This is the plasma that's like in your fluorescent light bulbs or on the surface of the sun or lightning. That's a whole different thing. But that just, it's funny. And that's why I really congratulate you all for like joining these, Ontario science students, because even scientists don't always talk to each other clearly, because the medical people have one definition of plasma and a physicist has a different definition of plasma. We need to be speaking the same language to really understand that. And finally, I was able to understand why they didn't understand what I was talking about, because they thought I was talking about blood the whole time. They're like, I don't know what blood has to do with it, because they saw this word plasma. So that can happen sometimes in science. So this can be done with nanosecond, picosecond, or femtosecond pulse lasers. So these are, lasers that are a billionth of a second long, or a trillionth of a second long, or I don't even know what that is, a quintillionth of a second long. Really, really short pulse of laser light is what you need, and that's why they're expensive. So let me just quickly take you through the physics, and you guys will love this because there's no equations, not a single equation in any of my talk. You don't need equations to understand any of this. I'm able to actually get first year physics students into my lab, and they can understand what we're doing. We don't need the physics, we don't need the math. So I'm just going to show you how this LIBS, so laser-induced breakdown spectroscopy, LIBS, up here. This is going to be a primer in 4 steps on what we're doing, and it's really not that complicated. So it starts off by shooting a pulse of laser light at a target. And we'll do that, as I said, we'll focus it through a lens, and let's just pretend that this is the red thing will be a laser light coming from top to bottom. The green thing is whatever you want, a chunk of steel. Let's just assume it's a chunk of steel. It's just easy for you to imagine that. So conservation of energy is really important. And I know for sure you guys learned about conservation of energy, because we just had a bunch of high school physics kids in here last week. They know about conservation of energy. You guys, I know, have taken at least 1 year of intro physics class. For sure, you know conservation of energy. It's true of laser light as well. I know in most of the homework problems you do, it's like roller carts rolling down an inclined plane or something, kinetic energy, potential energy. Yeah, but laser energy is energy too. And so when you shoot that laser energy into a target, and the laser does not come out the backside, because if you had a laser pointer, you could shoot it at the wall, the light does not come out the backside, where does that energy go? Energy was conserved. It had to be. So it went into something. And in this case, it goes into heat. The photon energy, the electromagnetic light energy, does not disappear. It's converted to another form of heat. And in this case, it's thermal energy. It's going to be heat. And so it starts to get very, very hot right under the area that the laser illuminates, not off to the sides, but right underneath it. And we say that that's where it's starting to absorb. That target is absorbing the laser light. And that absorbed energy in step 2 gets rapidly converted into heating. Heating results in vaporization of the sample. Oh, vaporization, you guys are going to like that. Why do I know you like that? Because you all also took a first-year chemistry class. And I know what we learn in first-year chemistry classes. We learn about vaporization, which is boiling. Sometimes in a physics class, you learn about the latent heat of vaporization, the latent heat of fusion as well, if you had the right kind of physics class. Vaporization just means their target became a gas. We call that ablation in our field. So ablation is the removal of mass when you just heat something up and all the atoms kind of come flying up into it. So ablation is kind of like the steam coming off a cup of coffee, but this is much, much slower. So ablation means that their mass used to be in the block and now it's going. And that just occurs when the temperature reaches the boiling point of the material. And you have to think from a chemistry standpoint, everything has a boiling point. I know you're not used to thinking of steel as having a boiling point, but steel has a boiling point too. You heat it hot enough, it melts, solid to liquid. You heat it even more, it boils, liquid to gas. Everything has a boiling point, even chunks of metal. And that's called ablation. So when that happens, you start to remove matter from the surface, and that forms a vapor cloud above. Because where's that vapor going to go? Just like the steam coming off your coffee cup, that vapor cloud has to sit above the surface of the metal. And so it sits here like that. And you're going to start to form a crater, like on the moon. You're melting stuff. You're kind of creating little fragments of stuff. You've got nanoparticles. You got microclusters. It's a very kind of complicated chemical environment. And it kind of looks like this. So here's some scanning electron micrograph images of the ablation craters I've left behind. These are some of the filter media that we shoot our bacteria on. You can see these beautiful little craters. Each one of these is where the laser has fired one time. And here's a zoom in on that. You can see it's just removed like a little ice cream scoop. It's just removed it out, but we didn't have to scoop it out. It all boiled out of there. When you do it on fingernails, it actually does not work as well at all, but it's the exact same laser shooting the exact same thing. But here there's no nice craters because the laser and the target material are not interacting very well. Here it is in a bed of Staphylococcus bacteria. Here it is on a piece of stainless steel. So wherever you shoot it, you're going to remove this little crater of material. And I want to do an analysis of that material. So how do I analyze that material? Well, that requires step 3, which is the formation of a plasma. This is where we left off the previous picture. This laser pulse is continuing to illuminate the vapor plume, but that vapor plume is getting more dense and more dense and more dense. And that's eventually going to lead to absorption of the laser light by the cloud itself. Some of those photons from the laser will get scattered. Some of them are going to be absorbed into the atoms. And that's just going to like create very strong local heating of that gas cloud, because eventually what happens is the cloud gets so dense with stuff you boiled off, the laser can no longer reach the surface. We call that laser plasma screening, plasma shielding, and you stop removing mass. And now all that laser light, the energy must go somewhere. Where does it go? It goes into that cloud. So that cloud of atoms is going to turn from a cloud at, I don't know, 5,000 or 6,000 degrees to a cloud at 50,000 degrees. And it's going to happen really, really fast. It happens almost instantaneously in a process we call electrical breakdown. And that's when this thing becomes a plasma. It kind of proceeds exponentially and just takes off and goes from a lukewarm cloud to a superheated cloud. And this plasma formation breakdown thing, if you've ever seen a lightning strike, which I'm sure you have, or if you've ever zoomed in on a spark plug and how a spark plug works, these are electrical breakdowns. So there's nothing unique about breakdown. A breakdown is just what's happening between the cloud and the ground. The electric potential there is so high, the electricity wants to flow and it just rips itself through the air by creating ions. Same thing with the spark plug. Ordinarily air is an insulator, but if you have enough electric potential, enough charge, it's just charge floating around, the electricity has to jump across that gap and it just rips things apart. It rips the electrons right off atoms and molecules. That becomes conducting. And that's what a plasma is. And you guys know how hot a lightning bolt is because look how much light it's giving off. That's basically what we're trying to do. We're creating little lightning bolts, but it's all caused by the laser and it's over much, much quicker than a lightning bolt. So that's accompanied by a supersonic shock wave. It's a kind of violent process. You'll hear it in a video that I'm going to show in a little bit. It's definitely loud. It emits a supersonic shock wave that starts to blow things off. And a supersonic shock wave is what thunder is, right? You guys have all heard thunder and lightning. So if there's lightning, there's thunder. In my lab, we strike a little plasma and it just makes a kind of tick sound, but that's the supersonic shock wave coming off it. And it's very, very hot. So things that are very, very hot give off light. And the light it gives off is kind of what we call white light. It's not useful. It's the pictures I'm going to show. It's just white light. It doesn't look too much like colors to you. It gives off a lot of light. It's really kind of bright. And so here's the video I'm going to show you. This is my graduate student, Jeremy Marvin, and my previous undergraduate student, Sydney Sleeman, who's now actually studying law. So again, your science degrees, super useful for all kinds of stuff. She's doing law at Western. And here they are. They're going to show you the plasma shooting on a piece of steel. And this is Jeremy actually analyzing the data. But now let me actually stop that share for 1 second, if that's okay, Griffin. I just want to make sure I'm sharing the audio on that, and I don't think I was. So share sound, do that, because I hate it when people do these things and they don't share their sound. Okay, so you should be able to hear this because you have to hear Jeremy. If you're not hearing them talk when I press play, let me know there, Griffin. So.
All right. Are you ready?
I'm ready. Oh, wow.
And there you can see it lighting up. And then here's the plasma. And you'll hear this spark. All right, now let's have a look what we got here.
Wow, that's really cool.
All right. Looks like we found gold.
Oh, really?
No, it's just steel.
Oh, okay.
So that's basically what the experiment looks like, and that's kind of what we're doing. So Jeremy's prospecting for gold in our little pieces of steel, thought we found something. He did not find it. But you saw that, and so you heard that little tick, and that's just the plasma. The plasma is way shorter than what you saw in the video because our cameras don't capture it well. It's just these little flashes of light, but you saw how bright it was, right? Everybody could see on the screen. That's really, really bright. That's a lot of analytic signal there. So that's what we want to do. If you guys, when we're done, if you want to see the rest of that video, just go to YouTube and search for Windsor Physics Rehse. That's me. You can see it's just a 4-minute video, and my students shot this all. It's a really good introduction to what we do at my lab here at the University of Windsor. So that was a project they had about a couple years ago. I said, put together a little video for me. And then this is my student, Emma, if you want to know more. So this is Emma. She was an undergraduate with me. Now she's a master's student. You can also, when you go to YouTube, check out her YouTube presentation of her, she won an award at this ICOPS conference last year for this little 15-minute presentation she gave on what we're going to be talking about today. So if you're cruising to YouTube and you're a better learner by like watching videos, I've got plenty of videos. You can follow up on this afterwards. So step 4 of this thing is the expansion and element specific emission. So like I said, it's really bright at the beginning. What we do is we wait for it to cool. It's actually so hot. It is like the sun, which just gives off a bunch of white light. It's not helpful. What we do is we wait some amount of time, like about a microsecond after that plasma, and then we look at it. And when we look at it, then enough of the electrons and ions and stuff are recombined, the atoms are de-exciting, everything's cooling down, and the light it gives off now is not white light. It's just specific to the atoms that are in the plasma. It gives off these narrow emission lines. And when we do that, I can analyze these narrow emission lines, which is called doing spectroscopy. And by doing that spectroscopy, I can measure exactly what atoms are in that plasma and in what condition they are in. And that's really what spectroscopy is. So it's bright enough to do spectroscopy on, and then we can do a lot of different things with that spectroscopy. So let's just talk about spectroscopy labs. So I have an expensive equipment for doing spectroscopy, but all of you are student scientists. We are going to do spectroscopy together. Spectroscopy is what I do. And it's funny because we always like to say, you know, before I became a spectroscopist, I couldn't even say that word. And now I am one. So spectroscopist is what I am. You can be a spectroscopist too, but say that word very carefully, please. And I'm going to show you 3 pictures of laser-induced plasmas, and let us see if the only tool you have for doing spectroscopy, which is your eyes, are good enough to analyze these plasmas. The plasmas are clear at the center of the screen. Let's take a look. Here's a plasma on the water. Here's a plasma on a piece of copper. Here's a plasma on a piece of steel. So my question to you, if I flick between these 3, can you all see any difference just in the color of the plasma, particularly between the copper and the steel? I think you can, right? This is quite blue or turquoise, and this is quite purple. You can see by eye the difference in the color, and that color tells you what the material is. So if your eye can do it, all you need is a really better instrument to do it, and then you'll be able to make really super sensitive measurements of exactly what elements are in that target. But even your eye is crude enough here to say, because the purple colors are different wavelengths than the blue colors, and those colors tell you what atoms are in it. So basically, you've just done right now what I'm doing for spectroscopy. We just have a more expensive machine to do it because our eyes are not great tools for doing that, but they're not too bad, right? Because you can see the difference of that. So if we take not our eyeball, but we take all of that color, say here, and we disperse it, all the light from the plasma, into its constituent colors, the RGB of the rainbow, and we plot the intensity of the colors that we see versus the wavelength, we get what we call a spectrum. And a spectrum just looks like this. So of course we're scientists. We take something that is beautiful and artistic like this, and we convert it to something that's kind of boring and not as beautiful, and we call that a spectrum. But that's what you guys have to do as scientists, right? This is the thing about science. We appreciate the beauty of it that's kind of what separates us from like artists and things like that, is we also appreciate the beauty, but we also want to say something quantitative about it, but we don't forget about how cool it is. And it's okay if you guys do experiments. We like to do it because they're kind of cool and they're kind of beautiful, and that's neat. That's a neat thing to do. And then can you appreciate the aesthetic of it, but still actually do the science of it? I think that's important, that scientists keep both of those thoughts in their mind. And so this is what a LIBS spectrum looks like. This is from a piece of steel. You can see all these narrow lines here. These are all the lines that come from different types of atoms in steel. And if I've done everything carefully, then the atoms that are in that plasma, which I can now measure with light, are the same as the atoms in the target. So by measuring the light, I'm actually measuring what was in the target. And then the size of those lines, which we call intensities, are related to the relative amounts of those elements, which are concentrations, which the chemist would be familiar with, the concentration of something. And so the software that I use to kind of collect this spectrum has this periodic table in it. And I can just query the periodic table and say, hey, here's the spectrum. What elements do you think are in it? And it's a piece of steel. So sure enough, we have a huge amount of iron, that's in steel. We have chromium, that's in steel. There's manganese, that's in steel. Some oxygen and nitrogen, because we shot it in air. There's some copper, some nickel, things like that. Palladium, ruthenium, molybdenum. These are all things that would be in an alloy, because steel is an alloy. And this is, so in a very simple way, in about a second, I can tell you all the different elements that were in that piece of steel. With a little more work, I could tell you exactly how much of each element is in that alloy, and then that would identify the alloy uniquely. So this actually technique is being used really well on recycling lines. When you have all kinds of metals in there and you don't know what they are, you can shoot this laser over it almost arbitrarily fast and exactly identify what all these different metals are. It's no problem at all on metals. Harder on bacteria, but easier on metals. So yeah, like I said, we just do a time resolved spectroscopy. You do need an expensive camera to do that. So the spectrometer I have has kind of an expensive camera, not strictly speaking necessary anymore, but that makes it laser-induced breakdown spectroscopy, or LIBS. So that's this acronym. So when you hear me say LIBS, I'll try to say it clearly. LIBS is an acronym for laser-induced breakdown spectroscopy. You fire a laser at a target, it creates an electrical breakdown, which makes a hot plasma, and you analyze the light from it. So that's what that means. I did not invent this technique, far from it. Doing a little historical context, the 1960, Myman invented the first ruby laser. About 2 years later, some researchers used that ruby laser to shoot it into a target and detect a spectrum from a plasma they formed with the ruby laser. So this is about 60 years ago. 2 years later, people basically invented LIBS. Again, not my idea. I'm not claiming it's my idea. You're going to see people all over the world do this technique. And then in 64, they did the first direct analysis. 65, they already started to develop theoretical physics models for the breakdown of a gas. So it's been around for about 60 years for sure. Why? Here is something I hope when you guys are getting the different talks and the different researchers, I don't know if anybody else has done this. This is a common slide that all researchers, at least in my field of physics, we like to show it. So you just go to Web of Science or you go to even Google Scholars or whatever, and you just kind of make a query to the publicized literature out there, and you see, show me the number of papers as a function of year for the field you're working in. And if you see this curve going up like this, for you as a student, this is a good thing. So when you guys are like looking at graduate schools, and you're like, oh, I really want to work with this person, you know, she's doing amazing work. But you have, I mean, you're not going to know what it is that she's doing because you're not really an expert, but maybe you could do something like this to see, are they in a field that's really growing? Is this getting exciting? Is this brand new? And boy, last 3 years ago, there were no papers and now there's 5 papers. And then this year there's 100. That tells you you're in a field that's really growing. That's going to be good for you, good for your employment later on. It shows you you're in an area that's vital and urgent and people are interested in it. Conversely, if you're in a field where like no papers have been published, means like nobody really cares, or if the number of papers has gone up and now it's on the decline, it means they're not interested anymore. It's just worth thinking about. And all of you in any field of science can do that as you're looking at research fields. So you can see that my field of libs, and right about before 1990, nothing, because the technology didn't exist. And since then, it's just been kind of going up, 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 and our field is now expanding globally, and it's all over the world. And the reason it's growing up, and if you want to talk to a professor and say, well, why is that? For our field, it's because of the applications, and it has advantages over techniques, and you can just apply it in so many fields. So now everybody's jumping into my field of libs. So the applications, I don't even have time to go through all of them. The applications really fall into one of two things. Once you get this lib spectrum, there are a whole bunch of people who want to quantify the amount or concentration of some element. So when I was at Wayne State, I was looking for lead in the highway roadside in Detroit. We used to drive cars long before you guys were born. We drove cars with leaded gasoline, it's called. It means they put lead into the gas, but decades of car exhaust put lead into all the soil on the edge of the highway. Not good for people. You can do this technique on paint in houses to see how much lead is in the paint. You could be analyzing alloys of steel. You could be analyzing precious metals to see if that gold you're getting is 24 karat pure or something else. That's one thing you can do. Or you could say, like in my case, I don't care what elements are present in bacteria. I want to know, though, is that pattern or ratio of elements repeatable enough to absolutely identify it, like for bacteria, like for cancer cells, like for conflict gems, for example, for different types of paper mulch, where I don't, so I'm never gonna like measure, oh, there's 5 parts per million chromium, nothing like that. I actually don't care what part per million anything is in my cells. I just want it to be reproducible and persist through time, and then it acts as a fingerprint, a reliable fingerprint that tell me it's what that thing is every time. So everybody in my field is doing one of two things. They're either trying to measure the amount of some atom, or they're saying, is the ratio of all the atoms together a chemical marker for this type of thing? So libs is particularly good at those things. So let me just show you some of the advantages that I think this method has. And I don't do all these methods, but you guys might. They might be doing it in labs at your university. You might go to a university where they're doing it. One of its advantages is you can do it on almost every element in the periodic table. There aren't really so many other analysis techniques to do atomic or elemental analysis that can do all the elements. There's something called X-ray fluorescence, which does a pretty good job, but not on the lighter elements. So we have the advantage where we can do light elements like hydrogen, helium, lithium, and we can do heavy elements like mercury, gold, and platinum. That's an advantage that not everybody has. We can do probably the best point sampling. So like I said, so when I focus that laser down, the plasma only forms where the laser spot is focused, and you can focus a laser pretty darn tight. So here I'm showing some data from a group in France who they're able to focus that laser down to like 20 microns. It's really small. And what they did with that then, if you see this image over here, this might look like a picture to you guys. This is not actually a picture. This is, I think it's probably a microscope image, but they've overlaid the microscope image with the amount of gadolinium or sodium that they saw in the lib spectrum. So it's a teeny tiny little laser spot, and they have rastered it over this mouse kidney. And the reason why it's interesting is they injected this mouse with gadolinium nanoparticles about a half hour before they had to sacrifice the mouse, and then they biopsied the kidney. And what they're studying here is the movement of gadolinium nanoparticles through the kidney tissue with extremely high spatial resolution. If you look at this picture over on the right, they're actually able to see the gadolinium nanoparticles diffusing into this kidney tissue. And this is an elemental map. This is not a photograph. This is just overlaying libs data on top of this kidney image. And so you're able to study in almost real time the diffusion of these metals through a target, and that's really interesting. You could also then scan it. So they have that layer. My laser shot, unlike the X-rays, don't go through a thing. It's just absorbed right in the first maybe micron of material. So if you do a raster scan over a whole surface of the kidney, then just do it again, and you'll get the layer underneath that. And you do it again, and you get the layer underneath that. And that's kind of shown up here. So you can also get depth profiling. So here's that same gadolinium of a kidney, I believe, but they're showing the different layers of it that they did. So again, kind of like using a microkeratome to like cross-section something, but they're not actually slicing it. You're just scanning the laser over and over. And each time it goes a little deeper. So you're getting depth information as well. That's a really cool advantage. It's very fast. In a second or two, we can detect things to about 1 to 100 part per million. I hope we have some kids who are working in chemistry labs on this call. Not as sensitive as the instruments you all use, definitely. We have way more sensitive instruments in any chemistry lab and here in our labs too, but it's super fast and you don't have to dissolve things in acids. So it has some advantages. You can make it wearable. That's a technology that not a lot of people have. So this is a prototype built for the Army. It's a CBRNE prototype. CBRNE stands for chemical, biological, radiological, nuclear, and explosive. These are the guys, the first responders who respond to any bad accident. And yes, there's more sensitive chemistry instruments down the hall, but you cannot put that in a backpack and wear that into an explosion zone. You can with our technology. And here's a prototype of them doing it. It's a guy using a laser to analyze this event of some spilled powder down here. And the results are being analyzed autonomously by a computer with the results displayed to his Google glasses to identify what that thing is. I'll come back to that. Here's another prototype that a different company made. So they're not the only people doing it. You can build high energy remote systems. So this is a system, again, I know there's more sensitive instruments down the hall, but this is something that they built to go in the back of a van. So what these guys are trying to do, if you look in this picture right out here, there's a little box that's at about 10, 20 meters. And so they're using this huge telescope and they're shooting this laser out of their box and they're trying to pick up explosive residue at 20-meter distance. So you don't actually have to go out and sample it. None of the other techniques in the bio or chemistry labs around here can you actually be in another room and do it. And you guys, again, you guys know this because you probably run some of these machines in the work that you're doing with your profs. You don't have to be anywhere near this stuff. You shoot out the laser, you stay safe. Maybe you have a piece of glass between you and it if it's a nuclear system. None of the other technologies can do that. We have commercial benchtop systems. So this would be familiar to you guys working in chem labs, working in environmental quality analysis labs, water analysis labs, bio labs. They would look like this. So we have companies that are starting to build these machines too. There are handheld units, which miniaturize everything into a little palm-held unit. This just runs an Android app that you can download the results onto your phone. So you can actually walk around and just zap things with your laser to tell in real time what those things are made up of. And so there's plenty of jobs working for these companies building this technology. So I'm just kind of relaying that not only is my technology interesting and relevant and kind of cool, but it's also very commercially available, which means, jobs for graduates who are in this type of field, which is a nice thing to know too. We've put a system on Mars. This is our biggest success to date. So this is the Mars Curiosity rover, a sketch and an animation. We don't have video of that. So this came from Optics and Photonics News. This is the cover story. They call it Zapping Mars, using lasers to determine the chemistry of the red planet. So this actually is the exact same technology that I'm using in my lab, but it's on the Mars rover and they're analyzing a rock. And you can, if I just go back and listen, you hear that sound again, the animation they were playing sounds a lot like what it sounded like in my lab. So this should just start here. Let's see. There it goes. Right, so that's rover firing its laser at these rocks on Mars. And it sounds exactly like what we do in our lab. On Mars, the system actually looks like this. So this is a beautiful piece of engineering and science. This is the ChemCam unit. So the ChemCam unit is this funny little head that most people think gives the Curiosity rover its charm because it looks like a little robot with a little head and an eye. Well, that head is actually the ChemCam unit. It's a high resolution imaging camera and a lib system. You take away the cool head of ChemCam and it looks like this inside. It's got a little telescope. The laser is going to come out through here, go off and shoot a rock. You take a very careful picture of it, and then you analyze the spectrum as well. This actually is the first selfie taken on Mars. For those of you who have not seen that picture before, this actually is the ChemCam unit on Curiosity. This is Curiosity taking a picture of itself. It's got a camera on the end. This is an arm that's going off screen here. It's kind of holding up a camera in front of it, and it's taking a picture back of itself. So this is the LIBS unit as well. And these are all the other instruments, but this is the LIBS unit on the Mars rover Curiosity. So it just again shows that the technology is very robust, it's very reliable. It's not a, it's definitely been proven. It's a proven concept. My lab doesn't look anything like the Curiosity rover because I run a giant research lab, so we don't try to miniaturize everything down. So this is a picture of my student Bo, who's now a graduate student at Guelph. And this is Bo. We have 2 tables full of equipment that actually do all the stuff that that rover did. This is multiple experiments, but again, this will look like a lot of labs you guys work in. It's not all a nice little unit, but that's the way research labs are. This is my student Laura wearing her cool laser goggles, and she's like trying to focus the laser in on some spot through a microscope objective. Here's just a little, again, this is a home-built chamber that we use to flush it with argon. We collect the light with some mirrors. The close-up of where I'm going to be doing the bacteria that I'll be talking about today looks kind of like this. So the lasers are over in the background here. This black box is the spectrometer. We collect all the light through this blue thing here, which is an optical fiber cable. We just have a home-built microscope here that I and my students have designed for zooming in on the stuff. And it's a whole table's worth of stuff, but it makes it very easy to introduce changes and do the experiments we want to do. So that's what it looks like in our lab. Gosh, there's so many applications. Again, this is why I have to say I love, so I'm sending 2 of my students and myself are going to a big, it's called SciX. It's just a large kind of science conference at the beginning of October. And I've seen people who are using LIBS to like identify where conflict gems come from. They can actually tell the mountain that a diamond was harvested from. Real-time sorting of waste and recycling being built in Germany for the assembly lines moving at meters per second. And this laser is just flying all over it, identifying every piece of metal in sight. There are people doing analysis on archaeological artifacts underwater. So when I go to a conference, I get to talk not just about the people doing LIBS, but I get to talk to people who are mineralogy experts, archaeological experts, tree experts, hematological experts. It's just, to me, that's really, really fascinating. I've actually supervised a student that's using it to look for gold. It actually is used to look for gold up in the northern parts of Canada, because you can take that little handheld unit and shoot rocks and look for the signatures that maybe gold is present. It's $1 billion industry, mineral exploration all over the world. And mostly it's so hard because you can't sample everything out in the wilderness. Online industrial monitoring, steel plants, steam plants, glass melt plants, nuclear plants. It's used just all over the world. The applications go on and on and on. It's really interesting. As I said, I'm interested in just, can we use it to identify bacteria? So let's just talk about that, because I don't have time to talk about all those other applications. So let me give you, I told you that I came up with this hypothesis in 2005. So again, for those of you who don't know, there has been one incident of bioterrorism in the modern age. So I'm sure all of you are familiar with the September 11th, 2001 World Trade Center attacks and the Pentagon bombings. But most people forget that there was a bioterrorism incident that occurred at the same time. A real sample of weaponized anthrax was sent to, here's the actual envelope it came in, Senator Daschle, that's at the Senate building in Washington, D.C. And I believe this is a picture of the weaponized anthrax powder. And a bunch of anthrax was also mailed to like NBC News or something like that. The problem is this is a pile of weaponized anthrax, which will kill you dead if you breathe it in. And then this is like a pile of cornstarch or flour. Can we tell the difference between those two? We cannot. That's a problem. This is where you guys and me and all of us with sciences degrees all of a sudden have our value, because these terrorist attacks happen. The US government looked around, and any government wouldn't say, okay, what do we have on the wings to tell this stuff which will kill you from this stuff which is flour and it's harmless? And the answer is nothing. And you know what happens when politicians want an answer and the answer is nothing? That means they start throwing money at things. And all this money came flooding into all these techniques for, like, right now, we need real-time anthrax detectors. And that kind of gave me the idea, because one of the hypotheses was, well, this laser technique could do it. And that's when I got really interested in it. And of course, you know, there's only been one bioterrorism incident and nobody died from it. And so you might say, well, Dr. Rehse, like, I don't really care about bioterrorism incidents. And I'll tell you the truth, neither do I. But here's the point. You don't need anthrax to conduct incidents of terrorism. So I'm just going to show you the front page of our local paper, which is the Windsor Star from very recently. Note these guys in the white suits, and these are the scuba gear. So these are the first responders, and they're responding to a potential bioterrorism threat. That's hazmat, right? Hazmat is short for hazardous materials. This is 2010. Somebody took it upon themselves to intentionally leave some white powder unidentified in a pencil case at the Solid Waste Authority. If you find white powder at the mall, at the post office, at the Solid Waste Authority, you have to assume it's dangerous. They have to call the fire department. The fire department comes out with their hazmat gear. They shut everything down for hours and hours. And then police have not yet determined the origin or makeup of the powder. It has been taken to a laboratory in Etobicoke for testing because they have no way of testing it on site. They come out in the hazmat, they sample it, they clean it all up. Maybe it shuts down your commute to work, 8 hours, 12 hours, who knows? No answer. Why can't these guys in the white suits tell you right now, no, it's powder, you're fine? Good question, right? Here again, 2012, same thing. Suspicious powder scare, empties building in downtown Windsor. And guys, this is just Windsor. This is one of the smaller cities in Ontario. Here's another one, another event. This is 2013, suspicious powder at National Bank, not dangerous. So what I'm saying is the threat of these events means we need the technology. I'm not particularly concerned about bioterrorism events, but yahoos who want the day off or something keep leaving unidentified powders all over the place. And every time that happens, the authorities must respond as if it's dangerous. And it costs money, it costs manpower, it's expensive, it shuts down businesses. We need better real-time technology that these guys in the white suits could wear into that containment zone. And you see how hard it is, right? They're changing in here. Like, you can say, oh, Dr. Rehse, we have better technology in our lab. Yeah, it's got to be runnable by a guy wearing these scuba suits. They got rubber boots on, they got thick latex gloves all taped up. Whatever you give them, it had better be really easy to use because they're wearing all this gear, right? So maybe something like this. I'm just saying, this has been built. This is the goal we're going towards. And so that's how I got interested in bacteria. And it would be great if we could screen everything for contaminations of bacteria. Part of my question, not a hypothesis, I just started to wonder, why do people still get sick if they're so good at finding bacteria? And we got dipsticks for COVID, and now you swab your nose for COVID, and there's dipsticks for E. coli in pools. Why do people get sick at all anymore? Why do they have food recalls? Why is there salmonella that makes us like recall produce and spinach and contaminated meat? Why? And I had to learn about this because I'm not a microbiologist. I'm not a biologist at all. So it turns out that, yeah, we have tools, but it's well accepted that the microbiological expertise and cost required to perform routine identifications preclude their common use as a screening mechanism to prevent human infection. So what it means is we have great tools at the hospital specifically for identifying bacteria. But in the hospital, it takes something like this to identify the bacteria. It's just expensive, slow, requires expertise. We want something that is cheap, fast, and requires no expertise. That's what does not exist right now. So you guys who are working on lab on a chip stuff, you know exactly what I'm talking about. This is the holy grail of modern medical science. Can you put all these lab things on one small little chip, or maybe you spit into it or put a drop of blood and it'll analyze it all like that? And these chips could be everywhere, cheap, disposable, safe. We don't have it yet, but many of us in science are working towards these things. And again, you guys too, I bet. So we are trying to not worry about the white powder. I'm not interested in the white powder. I'm interested in working with hospitals. So when you go in, say with a sore throat, can I analyze and identify strep throat right away? That would be my question. So we're doing things like trying to look for bacteria on the surface of things. So a lot of times you go into hospital and you can pick up an infection because your phone is contaminated. The bed rails, when you go to visit someone in the hospital, could be contaminated. You touch that, you touch your nose, you get sick with antibiotic-resistant bacteria. So we prepare bacteria as if a surface has been contaminated, like the remote control on the TV in the hospital, super contaminated, super dirty, don't touch those. they clean them, they try their best, but. And then also we're trying to simulate infections in clinical specimens. So a patient comes in and they give some blood, they give some urine, they give sputum, they do a nose swab or a cerebral spinal fluid from a spinal tap. Can we analyze bacteria in that? So I'm interested in clinical bacteria, the things that make you sick as a human. I work very closely with doctors and people in pathology labs to identify the open questions they have, and we're trying to simulate that environment. So we've come up with a way where we can collect bacteria, whether it's been distributed on a surface or whether it comes out of your mouth or your blood, and we put it into a centrifuge insert because we figured most people know how to run a centrifuge. I can train anyone to do that in just a minute. Every lab has those. It's not field portable yet. I admit that, but again, I'm trying to work in a hospital environment. They could probably get something, put it in a centrifuge, hit for 5 minutes to spin it down, and then all you have to do is put this into the laser, and that would kind of analyze it. So this is something that we invented. So what I like about being an experimental physicist is I build all of my own equipment, or a lot of it. So this is a thing that one of my master's students had to, like, he designed this, you know, in 3D AutoCAD or something, and we had it 3D printed. So this is a prototype device that we built. It does not exist anywhere in the world because I looked, nobody has these things, and it just goes into a centrifuge tube. And so you put all of the fluid that contains bacteria in this thing, spin it through the centrifuge, all the liquid goes to the bottom, all the bacteria get caught on this filter, and then we just shoot the filter with the bacteria, and then we can see, or we shoot the filter with the laser and we can see the bacteria. And it looks like this. We just take that filter off, double-sided sticky tape to hold on a piece of steel, very easy. Here's that Libs plasma, that bright spark on the surface of that thing. I look at the light from that spark and I can tell if there's bacteria in it and what type they are. That's the idea. That's the idea. When I do that, I get a spectrum that looks like this. So it's a pretty sparse spectrum, not a lot of lines, but the lines and the ratios of those lines tell me what bacteria are present. That's the theory we're working under right now. So this is like the data that comes out of that experiment. And then when I shoot the laser across the filter, it looks something like that. That's kind of cool. We built another device to concentrate all the bacteria are very small and they're spread over the surface of this filter. That's too much. We put it through a little cone. All the bacteria comes to that little hole in the center of the cone, and it kind of congregates right in the middle. So this is a way we invented to take all the bacteria in the liquid and make it go into one little spot. So when I hit it with the laser, it's much, much brighter. That works pretty well. And you know, this is what it looks like when we shoot the bacteria into those bacteria. So this little spot right here, this red thing, is kind of like a slime of bacteria. It's a lot of bacteria, but here it is when it's not so slimy. But when you zoom in with the SEM, you can actually see all those Staphylococcus cells in there. And then we blow them away with the laser. We analyze the light, and that tells me, oh, Staphylococcus, if we're lucky. How unique is it? Well, my initial test gave like really good ability to discriminate E. coli from staph, from strep, from mycobacterium, which is kind of a surrogate for tuberculosis, with like greater than 90% accuracy. It's pretty good. We're pretty good at it. Other people's have shown that you can discriminate antibiotic resistant strains. We've shown you can do strain classification. It's actually, it works pretty well in the idealized environment. Moving into the clinical environment has been very, very hard for me. We spend a lot of time, and Griffin will know this, a lot of time teaching computers to discriminate the bacteria from different, the spectrum from different bacteria. That's called machine learning. Another thing you guys could learn about, machine learning is in like every branch of science now. I know biologists who do it. I know chemists who do it. I know earth science people who do it. Computer science live in machine learning. If you want something to do in the 21st century, as you're looking forward to careers, try to integrate machine learning into whatever experiment you're doing. Meaning we're trying to remove the human from it because humans are fallible and machines are very predictive, but they're stupid. You have to teach them the right way. So what we do is we collect spectra from many, many, many known samples, as many as we can. So my students spend all day long shooting bacteria, and then you feed them into a computer. You're trying to teach the computer. What I'm showing here is like purple bacteria and green bacteria. Can we teach the computer to tell purple from green? Feed them onto a computer, and then you let the computer chew on it. And the computer will build a mathematical model. So it's all, there's mathematicians involved in this. They're building mathematical models. So it's all math for sure. And here's some complicated mathematical model. Then When you get an unknown thing, we call it a test spectrum. So now you've trained this thing in its math to tell the difference from purple and green. Then you get this unknown one and you say, hey, what is this unknown one? Well, you feed the unknown one into the model. The model will then predict the class membership. And you say, oh, that's a purple one. And you're right. That will be the idea of autonomous classification. We have to fingerprint spectroscopically all the bacteria that will affect humans, staph, E. coli, Pseudomonas, blah, blah, blah. Train the computer to tell them apart. And then when you guys or I go into the hospital room, they'll acquire the bacteria, shoot it with the laser, feed it into the model, and the model will tell them what it is, because no human can tell them apart, but the computers have really good predictive ability. So we've just shown that it's really sensitive and specific. It's robust and reliable through time. We've been doing tests for years on the same strains of bacteria, and that fingerprint is actually pretty reliable. So we've proven a lot of really cool things. You know, we're able to get stuff from urine. We can get stuff from about 500 different bacteria, not a single cell. I'm not that good yet, but maybe 500 bacteria. Different types of things that we can do. I'm finishing up now at 6 o'clock, so I know we're basically done. Let me just tell you what we're interested in now. Neural networks. This is that machine learning business. Neural networks are like in every branch of science I go to now, they're doing neural networks. Can you guys train a computer by building a neural network to do things better? If you're trying to classify, identify, predict, it's amazing how many branches of science it's in. So this is my undergraduate student, Grace Johnson, is working on neural network classification to do better classification, better than how we were doing it before. I've never done neural networks until the previous year. I'm seeing all this literature that says, wow, they're really good at telling these different lib spectra from each other and classifying things. We're trying to see if that's really true. We're very interested in the neural networks. Blood and urine. My graduate student, Emma Blanchette, we have a collaboration with the local hospital now where we're actually getting blood and urine specimens from the hospital, and we're obtaining bacteria from them. And these are some of the results of her tests. So she's doing lib spectra of sterile blood, bacteria in blood, and can we identify sterile blood that contains the bacteria? So when we test it, can it tell if that blood has bacteria in it or not, which is called sepsis, which kills you in about 24, 48 hours. Sepsis is very, very dangerous. And she's just showing that, yes, when there's bacteria in blood, I can immediately identify it. And this test shows when there's bacteria in urine, I can immediately identify that as well. We can detect with pretty good sensitivity several types of bacteria in blood and urine reliably to make a very fast test. So Emma's she'll be defending her master's thesis this fall, and it's all about this blood and urine and really trying to provide a tool to the hospital. The people in the hospital are really interested in this technology. And then the last thing we're interested in is nanoparticles. I have another undergraduate student, Emily Tracy. She's manufacturing nanoparticles in our lab, and we're trying to see if by putting the nanoparticles in with the bacteria, can we just make the plasma a lot brighter, which will then allow us to identify a lower number of cells, which would be better at then diagnosing you if you're sick and you don't have a high cell count. It's a whole new field for us. So the blood and urine is very new. The nanoparticles are new. These neural networks are very new. So I've been working on this, as I said, since 2005. There's still new stuff to do because we're not there yet. I'll be satisfied and done when we have like actual instruments in hospital pathology labs or maybe in nursing clinics or the walk-in clinics where they could quickly get a sample. I just want something where you can like do a swab, put the thing in there, and then they press a button, so that because the doctors are not going to know how to do all the analysis that we do. But if it's simple enough and you press a button, the computer will tell you what's in it. And that's where we're shooting for. We're getting there. It's a lot of fun. It's a lot of fun. So I'll conclude now. So this idea of libs, you've seen it on Mars, you've seen it on bacteria. So it provides an accurate, fast, highly spatially resolved, remote, meaning I can shoot the laser out to 10 meters, analysis of almost any type of target: solids, liquids, gases, powders, bacterial cells, clouds, gelatins, whatever you can analyze with this laser. It's got a very high degree of versatility because you can shoot almost anything. You can shoot your fingerprint and your fingernail. I've done that as well. It's very robust. It went to Mars, and that instrument worked perfectly up on the surface of Mars. And it's been adopted into many different interdisciplinary fields, including microbiology and medicine, which is what I'm really interested in. But you also saw archaeology, plant science, field science, water purity assays. It's everywhere. And the experiments that I do, which is why I really love them, involves a very exciting mixture of physics, laser science, computer science, analytic chemistry. That's a minimum. Throw in the microbiology of my stuff, throw in the health sciences. It's just a tool that we're applying in different places. So to me, that's really exciting. I love this interdisciplinary vibe that this field has. Some of you guys, whatever field you're in, you may stay in your track where I'm just doing chemistry and that's all I'm interested in. But when you branch out, and I'm a chemist, but now I'm going to be a chemist working in the wine industry, and I'm going to talk to the people who grow grapes to understand about that. It's so much more rewarding and interesting because you get all these different people talking to you, and it's so much better than just talking to people in your field all the time. I just love it. All this work has been funded since I've been in Canada by NSERC. I've been so grateful since coming to Canada from the United States. NSERC has supported me all the way. Canada Foundation for Innovation, the CFI, they've supported me, lots of great equipment. Ontario Research Fund has funded me, so thank you to the people from Ontario. University of Windsor has paid for so many of my students through this Outstanding Scholars Program. So all the students I was mentioning to you are supported through NSERC and also through my own university, where it has a program to pay undergraduates to do research during the year. It's absolutely awesome. And then here they are. So these are the people who did all the work. So here's Emma right there, and these people have been doing bacteria for a while. There's Sydney, who's now gone on to law. Chris was actually a computer science major. Paul was a medical physics major. They did all the work. Here was my 2020 research group. Here's somebody you might know. This is Griffin. He did 1 year of work for me on some of the data analysis, and some of my other people. They get all the credit for sure. Here's my 2021 group. There's Griffin again. We had a good time last summer standing around, and here we are just returning from our COVID lockdown. We're all wearing masks, but we were all in the lab doing experiments in 2021. Very pleased to be back and doing experiments. That was awesome. If you guys want to know anything more about this, or you're thinking, wow, that sounds cool for graduate studies, you know, you can just go to YouTube, Windsor Physics Research. I'm giving a presentation there. All the people at Windsor in the physics department who are doing research are in this video. If you want to learn more about my lab, again, go to YouTube, Windsor Physics Rehse. That's me. You'll give you a 4-minute introduction to what we do in my particular group, all narrated by the students, so it's very understandable. You might enjoy that stuff. So thank you very much for listening. Sorry, I went a little bit late, but I guess we got a little bit of a late start, but I am finished now. So thank you so much for hanging on, everybody.
Thank you, Dr. Rehse. I don't know if you have a few minutes, maybe we can take some questions in the chat here.
Yeah, for sure. Yeah, I'm not going anywhere. Absolutely. Yeah, I apologize for going over, but I hope, I don't know what the background of all the people on the call are, but I'm hoping that, I bet it's biologists and chemists and people. I bet they got a lot out of it, because there really is interest. You know, you could be a biologist and be using this field. I know them. You could be a chemist in this field and doing it, for sure. I know them. Earth science people, geologists, for sure. A huge amount of money in my field actually came from geology, because they are so desperate for an instrument to go out and analyze rocks in the field. You know, so it's everybody is in this. So I hope it was approachable to everyone in here, despite no matter what your background was.
Right.
Hello, Dr. Rehse.
Hello.
You can hear me well, right?
Sure, perfectly.
Okay, that's great. So yeah, I'm Mohammed. I'm a first-year student actually at Windsor, so maybe in physics as well. So
okay, well,
so we can probably see each other. That'll be great.
Yeah, for sure.
So my question is, based off my very basic understanding of high school biology and chemistry,
sure,
where cells are just a crap ton of carbon and phosphor and these various small hydroxyl groups and such. How exactly are you able to differentiate based off those chemical elements the different types of bacteria? Because in my mind, I would assume they would look the same, I guess.
Right. So I would actually say a cell is mostly a carbon-based bag of water. So a cell is mostly carbon, and if you're thinking atomically, hydrogen and oxygen. It's 99% water by weight. So the point is, we don't analyze, we see carbon, but actually that's not the main thing that we see. And we don't analyze water at all. So when we shoot bacteria, what we actually see is trace metals, which are not in the DNA. So it's a great question, Mohammed, because most physicists I talk to always ask the same thing. They say, well, geez, aren't cells all the same? It's like it's like DNA and stuff like that, macromolecules, organic molecules. For the people on the call who've taken organic chemistry, it's all those organic molecules. And what is an organic molecule? Oxygen, hydrogen, nitrogen, carbon. And guess what I do not analyze? Nitrogen, carbon, hydrogen, or oxygen. So 99% of the cell I just ignore, and I make a diagnosis based on metals and phosphorus. So phosphorus, carbon, magnesium, calcium, and sodium. These are trace metals that we see quite brightly. And so they seem to be different amongst different cells. So you have to do a little digging into what are these metals doing in a cell. And it turns out that they play a very important role metabolically and also for cell structure. So like in a gram-negative cell, which is what E. coli are, these metals are present in the outer membrane of a cell, and they're critical for controlling the packing of that cell. So every cell has these metals in just the right amount to regulate its function. And apparently that amount is different in these different cells that I can then pick up and tell A from B from C. So it's not at all clear that that's true, but this has been the research that I did to try to figure that out. I think that I was the first person in the world to publish a paper on why those elements should be different. And can you actually change the cellular chemistry by growing it on different medium? And is that change reflected in the cell? And it turns out it was. So we've actually done some microbiology experiments to tease into that a little bit. But so the simple answer, yeah, the simple answer is they are not just atoms floating around in the cell. They are there for a very specific reason. And that reason means the cell can only function if it has these elements in that concentration. And therefore they are unique to the cell and reproducible in every cell. Seems to be what's happening.
That is fascinating. Thank you very much for answering.
Thank you. I would say it's lucky. You say it's fascinating. I would say lucky, because if that were not true, it wouldn't work. But then that's okay. I would have proved it wouldn't work 10 years ago, and I would be doing something else, which is fine. But it works. What can you say?
Looks like Israel has a question there. Maybe.
Yep. Hi, Dr. Rehse. Thank you for the talk. It was amazing.
Oh, thanks.
This is more of a, I guess, biochemistry question, since
Yep.
I am in biochemistry myself. Since
Yeah, sure.
bacteria tend to have different stressors that occur to them so that they produce different proteins and concentrations, and
Right.
they have different growth phases, how does
Yep.
that work? If, let's say, you have like Streptococcus, one of them, and then it's under stress versus, and you're measuring that spectroscopy, how do you find the difference between that and like a regular one that's not stressed? And how do you tell the difference between the two? Or how do you tell that they're the same bacteria?
Okay. I actually glossed over that screen, but that was an experiment. And again, I'm the only person who's ever done the experiment. So one thing that now this is interesting, because this is actually an open source of debate. So I actually did the experiments that said the pattern that we were seeing was not dependent on how old the bacteria were. In the sense that we would harvest the bacteria, because we can train these computers to like tell the bacteria apart. So if something is different, my model will say, hey, this doesn't look like the other things. So we actually took bacteria, and we actually had a paper on the metabolic stressors, because we stressed them by putting them in an anaerobic environment and just kind of letting them sit with outside of their nutrient medium. And we tested after 1 day, 3 days, 5 days, 7 days. And we actually did not see any difference. And that, for us, that was good, because if that pattern changed all the time, you wouldn't be able to identify it. So that would be a deal breaker for you. We actually inactivated them with UV light, and that's an extreme stressor, because now they're not even reproductively viable anymore. And we were still able to identify them. It did not change the pattern much. We've autoclaved them, which we thought would be brilliant, because then all your bacteria would be completely biosafety level 1 safe. My initial work on that said it didn't change. And then another group published a paper and said, no, it did change. We can tell when they've been autoclaved. And then my master student, Dylan, did it, and he kind of was in the middle. He said it changed a little bit, but I can still tell that it's E. coli. So to me, that's actually a little bit of an open question. We have, and your question is so well posed, because I literally was just looking at a paper just a little bit ago where they were claiming that they actually could tell the difference between the different bacteria at different stages on the curve of growth, meaning the lag phase bacteria were very different than the log phase. I tend to doubt that because I did experiments where they were not really the same. I know that I always got best signal when the bacteria were reproducing in log phase, meaning, and I'm not exactly sure, that's not a biochemical thing as much as I think it's a physical thing. The cells maybe were more resilient. We would always get better spectra off, we call them fresh. I know that's not the right word, but when the bacteria were reproducing in log phase and not sitting around on a plate for a while, they seem to give really better spectra, but not appreciably different than something that, say, had been sitting on a plate for 70. So, you know, sometimes my students streak plates and they leave them like over the weekend or 4 or 5 days, and they're definitely not in log phase anymore. They still classify the right way. So I'm not really, here's the thing where I don't think I'm sensitive to that stressor, and I don't want to be, because I want it to always classify as what it is. One thing that's interesting from a biochemist point of view, we were trying to look for phage induction. So anybody knows anything about pathogenic bacteria, like E. coli, the E. coli that make you sick, it's actually a bacteriophage, which has inserted itself into the genome of E. coli. And that bacteria is only dangerous once the phage expresses and it starts doing something inside the cellular machinery. We were actually looking for signs of that biochemically. So we're actually, what you're talking about is I wanted to make this a tool for biochemists to probe the biochemistry of the cells as they're growing. I didn't ever see that. So I'm interested in that question as well. But I think we're just insensitive enough where I don't really see the difference of the different stressors, those protein stressors that are induced, because I'm not sensitive to protein content or any of those other biomolecules.
I guess then a follow-up question would be, if there's like 2 different strains of E. coli that are pretty similar, but we know that one of them causes pathogenesis once inside like human bloodstream, then if you're not sensitive enough, wouldn't you run the risk of not being able to detect the pathogenic E. coli?
Yes, I think that's absolutely true. That to me is surprising that you can do strain differentiation. For sure, because if you're not that sensitive, you should not be able to tell strains. And the most surprising thing is that people can discriminate strains. And I don't know what to say, because I did the initial experiments on a whole bunch of strains of E. coli, and 1 pathogenic and 3 non-pathogenic. And my computer model could predict them apart pretty easily. And then this other group did all the methicillin and the MRSA strains. That's not even me. And then some other groups have confirmed strains as well. So it apparently is sensitive enough to that. But if you then pressed me and said, well, then what is the elemental difference of the strains? I don't have the biochemistry to actually answer that, because I don't know, right? It's an easier experiment to like get bacteria A, B, and C, and I know they're different, and I employ microbiologists to grow them for me. And then we shoot them and train the model, and then you give me a true blind study. What is this? And the model predicts it 100% of the time. All I can say is it works, but then it's much harder to say, well, how does it work? I don't know. But it must be something to do with those inorganic elements that it uses. But how much diversity that could have, I wish I knew. But I can tell you one interesting thing. When I taught my model, I know it's doing the right thing, because when I taught my model on all these different bacteria and say, so here's 4 strains of E. coli, and here's Staphylococcus, and here's Streptococcus, and here's Pseudomonas, and here's Mycobacterium. And I said, it's all 13 different classes. And then I asked them to classify these things. It knew that they were all different, but the E. coli, it could tell, were very, very similar to each other. And I didn't tell them that. I told them these were like 13 different types of bacteria. And it said, no, 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 no. These 4 are all pretty similar. They're different, but they're similar. And it did that without us telling the computer. And I thought, okay, this is really working. And then the staph and the strep, which are very similar microorganisms, it said, you know what, these really look similar to each other. And I was like, yeah, they do. And so it's, as far as I can tell, it's a real biochemical difference that it's picking up on, but I'm hard pressed to say why. It's really interesting that it works. I'm really surprised that it worked that well in all those experiments.
Yeah, thank you very much.
Yeah, but my simple answer would be, I think membrane chemistry. I really think it's membrane chemistry more than anything else. I don't think it's inorganics floating around in the cytoplasm. I think these elements are present in every cellular membrane for a very specific region. And we have people like Drew Marquardt here, who's a biochemist at Windsor, and they study how the membranes let things through. Inorganic metals control that because they control where these porins form, and they control the integrity of how these, because a membrane is composed of really polar molecules and they don't want to stick together. And these elements are in there, and it's really sensitive to that. So maybe they have different amounts of that because the membranes are doing something different. I don't know, but my suspicion is membrane chemistry. I wish I knew more. I'm but a lowly physicist, so I cannot answer the question.
Okay, it doesn't look like there's any more questions, so I'll take this chance, I guess, to officially thank you, Dr. Rehse, on behalf of the Ontario Science Students Association.
Of course.
Your talk was much appreciated. So yeah, thank you for coming and presenting to us today. I have dropped a link in the chat for everybody to provide feedback for today's lectures.
Oh, that's great. Great.
Yeah. So thanks, Dr. Rehse, and we'll see everybody, I guess, later this week.
Right. Thanks so much for the invitation, Griffin. And like I said, I really appreciate all you people chiming in. And I hope, again, the whole point of this lecture, I really hope that you can see the connections between all these different fields. And, you know, you're all part of this association, but it's so great if we can all do work where a physicist can talk to a computer science and talk to a biochemist, and maybe they get a cellular biologist involved. And then they need a mathematician to do these models. There's no reason why you all couldn't be sitting at a table working on this one problem. To me, that's, I think, the best kind of science. And the fact that you're coming together talking about it now, you know, I think it shows that it can be done. It really can. So I hope you all stay interested in talking to people outside of your fields, because it'll pay dividends in the long run for sure.